Let's begin by looking at this particular limit of a trig function. And as we look at this one, if we were to substitute in a 0, we would get sine 0 over sine 0. Well, sine of 0 is 0, so we get something that's indeterminate. So L'Hopital's rule says that if we have a rational function that is indeterminate when we take the limit, then we're allowed to take the derivative of the top, the derivative of the bottom, and then take the limit. So this is not just taking the limit of that fraction. Because if we have a fraction, the derivative of that fraction, we would have to use the quotient rule. But what L'Hopital's rule states is that if we take the derivative of the top, so the derivative of sine is cosine times the derivative of the inside. On bottom, the derivative is cosine times the derivative of the inside. That if we take the limit, then that's going to be equivalent to the limit of our original, only if it's indeterminate. If this was not indeterminate to begin with, then taking the derivative of the top and then the bottom and then taking the limit would not work. So if we try to take the limit now, we would get, if we put a 0 in, we would get 2 times cosine of 0 on top, 5 times cosine of 0 on bottom. Well, cosine of 0 is 1, so we would get 2 over 5. So as x approaches 0, this expression goes to 2/5. But again, we can only take the derivative of the top and the bottom separately if our original limit is, or if our original limit by direct substitution gives us an indeterminate form. If we look at this one, by direct substitution, if we put in a 3, we get 0 on top, 0 on bottom, so this is indeterminate. In the past, we would just reduce this. We would factor out of 2. We would factor the bottom as a difference of squares. The x minus 3's would cancel, and now if we take the limit, we would get 2 over 6 by just direct substitution. But let's see if L'Hopital's rule works here. So since it was originally indeterminate, then we can evaluate the limit by taking the derivative of the top, the derivative of the bottom, and now plugging in our 3. So put a 3 in. 2 times 3 on bottom is 6. That reduces to 1/3. Yes, that does work. And the beauty of this is sometimes we get things that algebraically we might not have a very good way of reducing them or simplifying them into something that's not indeterminate. But often if we take the derivative of the top and the bottom, we will get rid of what makes us indeterminate. We will lose that discontinuity. This one, if we put a 0 in, we get the square root of 4, which is 2. 2 minus 2 is 0, and we would have 0 on bottom. So this is indeterminate. Let's keep in mind that this is 4 minus x squared to the 1/2 power. So applying L'Hopital's rule, if we take the derivative of the top, we get 1/2 times 4 minus x squared to the 1 less power times the derivative of the inside, and then the derivative of minus 2 is 0. On bottom, the derivative of x is 1. So this is just the chain rule for this. 1/2 comes down, do that to the 1 less power, multiply times the derivative of the inside. The derivative of that 0, the derivative of that is 1. This 2 and that 2 reduce. If we rewrite this, we're left with a negative x on top. We can call that the square root of 4 minus x squared on bottom. Negative exponent makes us go to the bottom, to the 1/2 means the square root. Now if we substitute in a 0, we get negative 0 on top, the square root of 4 on bottom. 0 over 2 is 0. So our limit actually comes out to be 0. We did an example probably similar to this back in Cal 1 when we were taking limits. If we were to plug an 8 in, we would get 0 over 0, so it is indeterminate. But the algebra on this was messy. And in fact, now that I look, now that I look at that, yeah, that still may give us problems. So if we want to do this using L'Hopital's rule, consider this 64 minus x squared to the 1/2. If we take the derivative of top and bottom, the derivative of the numerator is 1/2 64 minus x squared to the 1 less power times the derivative of the inside. On bottom, the derivative is 1. So this 2 and that 2 will cancel out. So if we rewrite this, we have a negative x on top, the square root 64 minus x squared on bottom. Now by direct substitution, we get negative 8 on top, the square root of 0 on bottom. That's not indeterminate. That's actually undefined. So this limit does not exist. And it's going to ask us, in which way does it not exist? Remember, there are different types of when limits don't exist. Some are when the two ends go somewhere differently. Another one is when we're going either to positive or to negative infinity. So at 8, we essentially are going to have an asymptote. If we're approaching 8 from the left side, so if that's 8, if we pick a number like 7 or something and plug in, we would get a negative number on top. When we plug a 7 in, we're going to get something. We're going to take the square root of that. That's going to be a positive number. So a negative number over a positive number is negative. And as the denominator is getting closer and closer to 0, the answer is getting closer and closer to infinity. You could plug some numbers in like 7.9999, and it turns out this number is going to be getting bigger and bigger and bigger in the negative direction. So it doesn't exist, that is true, but the way it doesn't exist is because our answer is getting closer and closer to negative infinity. All right, let's take a look at this one. By direct substitution, we would get arc sine or inverse sine of 0 on top, 0 on bottom. And if you just take your calculator out and you try to take inverse sine of 0, that's 0. So we have 0 over 0. This is another indeterminate form. So since it's indeterminate, we can use L'Hopital's rule. The derivative of the bottom is just 1. The derivative of the top, remember when we take the derivative of arc sine, u, we get u prime over the square root of 1 minus u squared. So 4 over the square root of 1 minus 4x squared, which is 16x squared. So u prime, that's u, so u prime square root of 1 minus u squared. So if we simplify that, that's just 4 over the square root. we let x be 0, we would get 4 over the square root of 1. So this approaches 4. So that's our limit. Once we get something that's no longer indeterminate, we cannot use L'Hopital anymore. And then let's do this one. If we were to plug a 0 in, we would get 1 plus 1 over 0 to the 0 power. Now let's think about this one. If 1 over 0, that's undefined. If we think about letting x get closer and closer to 0, if we divide 1 by a bigger and bigger number, or I'm sorry, a smaller and smaller number. So if we divide 1 by 0.1, we get 10. 1 divided by 0.1, we get 10. If we do 1 divided by 0.00001, that's getting bigger. If we do 1 divided by an even smaller number, that's getting really big. So the inside of this parenthesis is going to infinity. And then we're raising that to the 0 power. Now most numbers, when we raise them to the 0 power, we get 1. But also notice we're letting x get close to 1. So our exponent is not making it all the way, I said getting close to 1. X is getting close to 0, not close to 1. So notice our exponent is not actually all the way to 0. We're getting closer and closer and closer to 0. Which means we might almost have infinity, and then we might have 0.1. Or we might have almost infinity and have 0.01. Well, that's, if you have an exceptionally large number, but raise it to a power, what is that going to do for us? So this is actually going to be, when we have infinity to the 0 power, that's actually an indeterminate form. Now, in case you see something like this, if you have 0 to the infinity power, that's not indeterminate. Why is that not indeterminate? It doesn't matter how many zeros you have. If you have 2 zeros, or 500 zeros, or an infinite number of zeros, 0 times 0 times 0 times 0 times 0 forever is always going to be 0. 1 0 times anything is 0, much less an infinite amount of zeros. So the first thing here is that this is indeterminate. Okay, so then how do we do this? Because looking at it, this doesn't look like just a simple rational function. It's not just a basic fraction. So how do we evaluate this? So let's call our answer y. So when we evaluate this limit, that answer we're going to call y. When we have a variable in the exponent, recall something that we've done before is we've taken the natural log of both sides. Because if we have natural log of something, if that something is raised to a power, we're allowed to bring that exponent down. For properties of limits, we can do the composition first and then take the limit at the end. So instead of doing the limit and then doing the composition by plugging that into natural log, we can plug this into natural log and then take the limit. Natural log of 1 plus 1 over x to the x. So natural log y equals the limit of, since we have natural log to a power, we can bring that x down, and then we can do that times natural log. Hold up a minute. We said to do L'Hopital's, we have to have a fraction. We have to have a function on top, a function on bottom. And while we do have a fraction here, that's just inside our function. That's not a function to a power. So how do we make this into a fraction so that we can apply L'Hopital's rule? Well, we can do this. We can leave natural log on top, and multiplying by x is the same as dividing by 1 over x. So instead of multiplying by x, divide by 1 over x, now we have a fraction. Now we have a fraction. So let's call this 1 plus x to the negative 1, and let's call this x to the negative 1. This is still indeterminate. Still indeterminate. So using L'Hopital's rule, we would take the derivative of the top. Well, when we take the derivative of that, we would have 1 plus x to the negative 1 on bottom, the derivative of 1 plus x to the negative 1 on top. So if we take the derivative of what's inside, we would get negative 1 x to the 1 less power. That's just u prime over u. So that's the derivative of natural log. When we take the derivative of the bottom, we get negative 1 x to the 1 less power. So we did the derivative of the numerator, and then we did the derivative of the denominator. So let's simplify this. So we have negative 1 x to the negative 2 over 1 plus x to the negative 1. Instead of dividing by that, let's multiply by the reciprocal so that we can see that those cancel. So we have the limit as x approaches 0 from the right side of 1 over 1 plus x to the negative 1, or we could call that 1 over x. Now, it would be tempting to say, oh, let's do L'Hopital again, because the derivative of the top is 0. But is this going to be indeterminate? And the answer to that is no. If we let x go to 0, the numerator is 1. What about the bottom? If we put a 0 in on bottom, 1 divided by 0 is undefined. But also keep in mind, as x is getting close to 0 from the right side, this is getting closer and closer and closer to positive infinity. As we demonstrated a minute ago, if we have a denominator that's getting closer and closer and closer to 0 from the right side, so positive, then that fraction is getting closer and closer to infinity. Well, if we have 1 and we're dividing 1 by positive infinity, 1 divided by positive infinity is essentially 0. So we're essentially going to 0. So that limit of that whole thing is not indeterminate, it's 0. So we get not that our final answer is 0, but natural log of our final answer is 0. If we want to get y by itself, we do e to both sides. E to a natural log undoes each other. E to the 0 is 1. Remember, y stood for the answer to our original problem. Y is whatever that limit is. We got that y equals 1, so that means our limit, as x gets really close to 0, the limit of that is 1.